recorded lectures on topics. This one was design of beams, and yesterday I uploaded design of beams continued. So there is a lecture on I would say 2 hours lecture, online recorded lecture on the topic which today I want to discuss. Actually, there are few slides in which I discussed in detail, which are recorded in this video lecture. So today I want to just skip few of the slides because you can watch those slides later on, and I just want to apply the information discussed in those slides to solve one design problem. So I recommend you to please watch all the recorded lectures which are present in your folder. In addition to this video recording, I have also uploaded in your files folder in the class material design of beams, the PDF file of today's lecture. So please read this PDF file as well and also watch the recording. So in this design of beams, recorded lecture, I want to discuss first estimation of load on the beam and then finally to design it. As up till now we discussed analysis and design of rectangular singly reinforced beams, and in our discussion we considered for design problems a directly given uniformly distributed load. So there was no discussion how we got that uniformly distributed load. So in today's lecture we want to first estimate the load carried by the beam, and then after getting load on the beam we want to design it. And one actual slab system in which beams are present, we want to solve that kind of problem, that a room slab and that slab has beams. So how much load will travel from the slab to the beam, and then after getting uniformly distributed load on the beam, the design as you are familiar with direct design by calculating rho of tension control under reinforced beam and then designing it accordingly will be repeated. At the moment 22 students are online. Let me start the recording first. Three students are visible. So let me just quickly review the slides. As I said that please watch the recorded video present in your folder in which I explained these slides from slide 2 to slide number 11. Slide number 11 I discussed in detail in that recorded video, and then actually onward I want to discuss these slides in today's lecture. So just I want to give you what was the outcome of this discussion. Actually, if beam is present in a one-way slab system, so this picture on slide number 2 indicates that there are two panels which are adjacent to each other, and there are four columns, and on column center line beams are running, and there is also one beam present which is resting on the spandrel beams. So you may call it a secondary beam which is resting on the primary beam which is running from column to column. So it seems that there are two panels now which are resting on these beams on the perimeter, and if we measure the dimension center to center of the beam which are running on column center lines, or this secondary beam which is present, which is dividing the center to center distance of column exactly into two sub panels. So that dimension is then L with subscript X. So this is actually the dimension center to center of the two parallel beams, and it is the shorter dimension of this one panel, and the longer dimension of this panel is L with subscript Y. So there are two panels and their dimensions are Ly into Lx. Ly is the longer dimension and Lx is the shorter dimension. If I divide longer with shorter dimension and my answer comes out to be equal to or greater than 2, then this slab will be one-way slab. So it means the slab behavior will be one way, its load distribution will be one way, its bending curvature will be one way, single curvature. And it will distribute its load to the supporting beam 50-50%. So this one panel, its 50% load will go to this beam, which is along the longer dimension of the panel, and 50% load will go to this beam. And same is the case in next panel, that 50% of its load will be transferred to this beam. So it means this interior beam, it is carrying 100% load because 50-50% from adjacent panels. So simply we can say that if I have the pressure value known on this slab, I can multiply that pressure with the transverse dimension, which in this case is Lx, because Lx by 2 from adjacent panels. So total it will become Lx. So the pressure on this slab, which is shown in hashed area, into Lx will give me the load uniformly distributed on this beam. So first thing is how to get this pressure. I mentioned in one of my lecture that if you are provided with the thickness of the slab, actually the thickness of the slab will be your first step when you will design the slab. So decide the thickness will be your first target. So when we will discuss design of slabs, you will first fix the slab thickness. Here, since we are at the moment discussing beams, so if we know that this slab has the thickness 150 millimeter, which is the H of the slab, and furthermore, above this slab, there is a floor finish. We have the architecture working drawings, and from section, we got idea that the floor finish proposed by the architect is of thickness 100 millimeter, which might be a composite of brick ballast and terrazzo or some PCC and tiles. So it depends on the selection of the finished materials which are superimposed on the slab. So if from the architecture working drawings, we have the idea of floor finish and the thickness decided by the structural engineer are known to us, then I will convert them into pressure by multiplying with the thickness the corresponding densities. For example, reinforced concrete, we will use for reinforced concrete a density of 2400 kg per meter cube. And for PCC or the, I would say, floor finish, a good selection will be that we might consider the density around 2300 kg per meter cube. So since these densities selected are in terms of kg per meter cube, so I will divide the thickness with 1000 to convert it into meters, and the finish thickness also by 1000 to convert it into meter. So then resultantly, I will get thickness into density, the answer in kg per meter square. So can you respond me that what you will get 150 over 1000 into 2400 plus 100 divided by 1000 into 2300, how much will be the service self-weight pressure? Can you calculate? Please use your calculators.
Sir, 360. First
Good.
one, 360.
Okay, total 150 and plus 100, both for.
No, sir. Total. Let me check it.
Okay, if you are breaking up into two, 150 divided by 1000, 2400, 360, and then plus
590.
total 590. Okay.
Yes.
So total comes out to be 590 kg per meter square. And this 590 kg per meter square, I have one, I would say, the service self-weight pressure, which I may assume is present in this hashed area, which is supported by this interior beam. Now, if I will multiply this 590 with the transverse dimension of this area, which is Lx, I can get the UDL on this interior beam. Just for sake of discussion, if I propose you that let's assume Lx is 3 meter and Ly is 8 meter. So Ly over Lx ratio then will come out to be 8/3. So it will give you idea it is greater than 2. So it is one-way slab. So on your working drawing, you can easily decide that this is a slab system which is one way, and for this interior beam I have to calculate the loads by using the transverse dimension multiplied with the pressures to get the load on the beam. So for this 590, then I will multiply this with 3 meter to convert it into UDL. So that can be done to calculate the service load due to self weight only on the beam in terms of then kg per meter. So this is one, you can say, one of the step to calculate the self weight UDL on the beam. But actually we are not having only the dead load or the self weight, we also have the live load. So based on the structural use information regarding the type of the building, what kind of occupancy we must select, we can decide the live load. Suppose it is ordinary residential building and for such buildings we can check from the guidelines what are the live loads suggested for such type of buildings. For example, for this room slab, I propose that the live load proposed is 300 kg per meter square. Very commonly used live load for ordinary buildings, residential or commercial. So if 300 kg per meter square is the live load, so you will notice that they will provide you live load directly in terms of pressure. Yes, thicknesses or the self weights we need to calculate by converting by multiplying the thickness with the densities, but pressure live load information is directly given in terms of pressure. So we will then be adding up dead and live loads to get the total load on the slab. And then finally, I will multiply them with the transverse dimension to get the total service load on the beam by selecting the combination. Since we are working on ultimate strength design, and the second combination of ultimate strength design will govern in this case. So 1.2 dead plus 1.6 live, I suggest that this combination will govern and this will give us a maximum ultimate load on the beam. So then what I will do, I will multiply the calculated 590 with 1.2 and plus then 1.6 into the selected service live load on the slab is 1.6 into 300. So this together then will give me ultimate load by combinations 2, second one on the slab system. So can you calculate this 1.2
Sir,
into 5?
1188.
It comes out to be 1188 kg per meter square. Now this 1188 is ultimate pressure, which includes dead and live. So we normally use kilonewton rather than kg in our calculations. So I can convert this kg into kilonewton by multiplying 1188 with 9.81 to convert it into Newton, and then dividing it with 1000 to convert Newton into kilonewton. So it then comes out to be around 11 point, how much?
11.65.
11.65 kilonewton per meter square. Don't forget that this magnitude is very commonly calculated magnitude on slabs, 11 to 12 kilonewton per meter square. In SI system of units, the pressures ultimate which you will mostly use will be around 11 to 15 kilonewton per meter square on normal slabs of thickness around 150 millimeter and ordinary finishes of 100 millimeter thickness and normal live loads, not very extraordinary heavy loads like on warehouses or godowns where live load proposed will be higher. But for ordinary residential or commercial buildings, this is very common value. Rather you use 116 kilonewton per meter square, that will be one unusually high ultimate pressure. So then recheck your calculations, there may be somewhere mistake. So it is then decided that for this slab system we are having about 11.65, or let me round up to, it is having 12 kilonewton per meter square ultimate pressure. Now I can multiply this resultant pressure with the transverse width, because I have decided that based on aspect ratio it is one-way slab. So this ultimate pressure multiplied by 3 will give me UDL on this beam. So this beam, which has a span 8 meter and it is resting on other beams, spandrel beams. So this is a secondary beam and it is resting on this primary beam. So this can be considered as a beam which is secondary and resting on the primary, or you may call them spandrel beams. So just if I assume that end conditions are still simply supported and I am not having any negative movement finally at the end of the beam, or I am assuming at the moment these ends are free to rotate, so then I can say that 8 meter is the span of this beam and this beam has the UDL on it equal to 11.65 into 3. So how much is the result? 34 point something.
So 34.95.
34.95 or 35 kilonewton per meter is the ultimate load on this beam against which you will design this beam. Since you are assuming at the moment that end conditions are simply supported, in next lectures we will discuss the movement coefficients or what might be the restrainment at the ends, and then there may be a chance that the ends will hog and negative movement will come at the end. They are not fully fixed, but they are partially fixed. Then obviously we might not be considering that the bending moment diagram is WL square by 8 or it is simply supported beam. Then there may be a choice that at the ends assume the negative movement as WL square by 24. It is just one, you can say, option with what we can select based on end conditions. That end will have a hogging movement and we will have a then point of inflection somewhere, and then the mid span will get the moment magnitude not WL square by 8, maybe WL square by 16 or 14. So in this way, in next few lectures we are going to discuss these points, but at the moment you can assume that this single span beam is resting on spandrel beams and movement is released, so they are acting like simply supported. So 34.95 or 35 kilonewton per meter will be used to calculate the mid span maximum movement. And as you are familiar with the simply supported beam movement magnitude, so you will use WL square by 8. And the rest of the procedure will be same as we have done such kind of design by using ultimate stand design methodology. Once we are given with WU and we know the FC prime and FY, and or we decide from our you can say knowledge about the type of building, what should be the FC prime, what steel grade we will recommend to the client for this building, and obviously based on material strengths and known calculated ultimate loads, we can design the beam. First thing will be to proportion the beam, to size the beam, and then to calculate the area of steel. And all this discussion up till now was to get that load on the beam from the architecture working drawings, where we are given with the structural scheme that where are the columns, what are the spacings between them, what are the room sizes, and knowing the dimensions, we actually decided the load transfer paths, and accordingly we selected the type of slab, and this amount of work will be done to determine the load on the beam. There are two statements given underneath that if we are having the exterior beam and we want to design it, at the moment I discuss interior beam. For exterior beam, since there is a edge present and there is no continuity on this side, no cantilever is present, neither a cantilever nor a shade. If there is some cantilever on this side, beam has some projection beyond the edge, then this cantilever, and suppose if this cantilever projecting out is 1 meter, some buildings have some projections beyond the exterior face, then that cantilever width will be included into the influence area or the transverse. Actually, at the moment we are working on the calculation of the transverse width, which will be multiplied with the ultimate pressure. So for the edge beam, sorry, this should be the not interior, exterior beam. So for the edge beam or exterior beam, PERIOR. So for the exterior beam, 50% is actually Lx by 2 present. And then if suppose there is a cantilever present and it has the length 1 meter, so that 1 meter will be included into that Lx by 2. So it means for this particular problem, it will be having Lx by 2 1.5, then plus 1 if it is a cantilever present. Then it means I will multiply the ultimate pressure with 2.5 to get load on this exterior beam. For interior, I use 3 meter because the adjacent spans were equal and they were having 3 meter shorter span. And in this way, we need to estimate for interior and exterior what are the transverse widths which will transfer the load to the beam. Same kind of effort is required when we are having slabs in which bending curvature will be two-way, in which load distribution will be two-way. And we can classify such type of slabs simply by taking the aspect ratio longer over shorter dimension. And if it comes out to be less than 2, although it is shown equal to or less than, and for one way it is given greater than or equal to 2. So it means equal to 2 is almost on the bound. It is almost having the behavior predominantly one way. So you can say that if it is aspect ratio is less than 2, the slab will be two-way and the load distribution will be two-way. So how we will estimate the load on the supporting beams? For example, in this picture, there are 9 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 columns and each panel, there are 4 panels, and each panel has the shorter dimension Lx, longer dimension Ly, and aspect ratio is less than 2. Just for example, I may propose you that Ly assume is 5 meter and Lx assume is 3 meter. So 5 over 3 will give you the answer less than 2. So it means the information is it is two-way slab. For two-way slabs, you will radiate out line from corner at an angle 45 degree. From each corner, if you will radiate out line at an angle 45 degree, and where they will intersect, you will join them by the straight line. So if the aspect ratio Ly over Lx will be 1, panels are square, you will get for each panel 4 triangles, because once you will radiate out at 45 degree lines, if panel is exactly square, you will not get any trapezoid, so it will be total 4 triangles. Here, since it is 5 by 3, we will get 2 trapezoids and 2 triangles. So it is then decided that the longer span beam will take the share of trapezoid if it is exterior beam, and if it is interior longer span beam, it will take the share of load from true trapezoids, and the shorter interior will take the share of two triangles, and exterior one triangle. So it means that if I am designing the interior beam and it is a two span beam, because there is a column over here, so I can sketch that there are triangles present on these beams, and since there are two triangles, so this multiply with 2. So there are two such triangles which are present on this beam of span 3 meter. And if I'm sketching this a long span beam, I can say that an interior long span beam, I can sketch like this, that there are two interior long span beams, each of span 5 meter, two span beams, and they are subjected to two trapezoids. So it means into 2 because they are interior. If it will be exterior, then it will be 1. If this comes, we are discussing the exterior short span beam, then there will be one triangle in each span. Now here the problem is little tough, tedious, because you need to draw the bending moment diagram for a beam which is subjected to triangular load or trapezoidal load. And if end conditions are simply supported, again the mid-span will be having maximum sagging moment. So the mid-span moment ordinate is important here. Now it is not WL squared by 8. So you need to write the equation, and then with little more effort, you will get the mid-span moment. So in these slides, which I have recorded with section D, and I have uploaded on your folder. So please watch that recorded video where I discussed finally how to convert these triangular or trapezoidal loads into equivalent UDL, so that finally the answer which I get for the mid-span maximum movement is same for both of them. So what is discussed in this first few slides is how to convert the actual triangular diagram into equivalent UDL, so that finally the movement diagram from this picture and from this simplified one, the movement ordinate remains the same. So this is actually discussed in the next slides. To calculate that transverse width, which I will multiply with my ultimate pressure. For example, if there are two trapezoids as I'm hatching them, and I know the ultimate pressure on these two trapezoids, as I did the calculation for one-way slab, and I got the idea that the pressure is 11.65 kilonewton per meter square. So in the previous example, we have calculated this for one 650 millimeter thick slab and 100 millimeter finish and 300 kg per meter square live load. Suppose for this slab, floor finish and slab thickness and live load is same. So we will get the same ultimate pressure on this slab, 11.65 kilonewton per meter square. Now the question is how to convert this pressure into UDL for this interior long span beam. So I must multiply this pressure with such equivalent width, which will convert this pressure into equivalent UDL. And the answer which I will get is exactly same what I will get otherwise by solving the beam subjected to a trapezoidal load. So that equivalent width for trapezoids and for triangles has been explained in the next slide. So I will just discuss with you the outcome that equivalent widths to be used for triangles and equivalent widths to be used for trapezoids to convert the ultimate pressure into UDL is for triangles that equivalent widths will be 2 by 3 LX if this is a beam which is interior and it has two triangles. If the beam will be exterior and it has one triangle, then exactly half of it will be the equivalent widths and it will drop to LX by 3. And if exterior shorter span beam has cantilever, it will be added directly into the equivalent width. So this equivalent width derivation is explained in that video lecture. So please watch that video. The result is, for example, let me apply this 2 by 3 LX to this beam. Let me first hatch this. So I'm now talking about this beam. So if I say that this beam is having a two triangles and it has the span 3 meter, I am now converting it into a beam which has the UDL, and answer I will get the same. What I will do, I will and for this beam the pressure was suppose on this slab system was 11.65 kilonewton per meter square. So what I will do, I will multiply 11.65 into 2 by 3 LX, and LX here is 3 meter for this slab system, because slab system has always shorter span will be notated with L subscript X and longer L with subscript Y. So 2 by 3 LX means 2 by 3 into 3. So the result will be 11.65 into 2. So it means the interior short span beam is subjected to around 13 point something kilonewton per meter UDL. And this is how quickly you got the UDL, and this UDL you can use to calculate the moment rather working on this triangle and calculating the mid-span movement. You will get exactly the same answer if you will use this equivalent width. And in the derivation, we have discussed this calculation of 2 by 3 Lx. And if it is in exterior beam, it means it is Lx by 3, one triangle. And for trapezoids, derivation finally tells us that if it is interior long span beam, the equivalent width what you will use to determine the UDL on the interior long span beam will be Lx into 1 minus r square over 3. And it is important to note that whether it was short span beam or the long span beam, in the calculation of equivalent width, Lx is appearing in both equations. So some students, they commit this mistake that while applying it for long span beam, they get confused and they use Ly over here. Don't forget that in both derivations, final outcome will be that in calculation of equivalent width, Lx is appearing, is involved in calculation of the equivalent width, and it will be proved when you will go through this derivation. In this, you can say final equation of equivalent width, R is actually the aspect ratio, and don't forget that here R is shorter over longer span. I mentioned to decide the one-way, two-way slab, and you can divide longer over shorter, and if it is less than or greater than 2, you can decide two-way or one-way slab. Here in this equivalent width equation, R is actually arranged as shorter over longer, Lx over Ly. Even to classify the slabs, you can take the ratio of shorter over longer. And if shorter over longer, as I said, longer over shorter greater than 2, if it is, then it is one-way slab. So if I will reverse this, it will become shorter over longer, it will become 0.5. Then accordingly, you can decide that if shorter over longer is less than 0.5, for example, I may say 8 over 3 was greater than 2. Now, if I say 3 over 8, it is less than 0.5. For both cases, it is one way. Longer over shorter greater than 2 or shorter over longer less than 0.5, it is 1. And vice versa, that if it is less than 2 or it is greater than 0.5, it will be two-way. But in this equivalent width derivation, you will get R as the ratio of shorter over longer. And for our example problem, as I selected Lx 3 meters, 1 minus R, I selected 3 over 5 as the Lx and Ly. I will take square of it, then divide it with 3. And what will be the equivalent width for our assumed panel? Can you calculate? 1 minus 3 और 5 कैलकुलेट कर
Sir,
सकते हैं
2.64.
Good. 2.64 or 1, right? So it is important to note that this equivalent width will be multiplied with 11.65 if for this slab system you have estimated the ultimate pressure. It will give you the UDL on this beam. It is important to note that had it been one-way slab, then obviously you will use over here the distance center to center, then 2.64 will increase to 3. 3 as we did in our first example, that it was 8 by 3 and the total center to center was the load transfer to this beam. So rather than getting triangle near the ends, we are getting the full width effective. So it actually in two-way slab, since the load distribution is two-way, so we dropped the equivalent width from 3 meter to 2.64 meter, because now the load distribution is two-way. So some load will be transferred to the short beam, and which we have estimated that 2 by 3 Lx will be the load which will travel to short beam, that this equivalent width will be used to determine the load transferred to short beam, and this equivalent width will be used to determine the load transferred on long beam. So these first 9 slides are actually to derive these equivalent weights to determine the load transferred on the short or long uh, long span, you can say interior or exterior beams. So let me stop here for few minutes and then I will resume the lecture after 5 minutes, right? In next slides, I discussed in that online recorded lecture, what if wall is directly resting on the beam, and then on slide number 11, I discussed how to estimate load uniformly distributed on a short beam, which is the beam placed over openings like lintel, named as lintel. How to estimate load if that lintel has brick courses above. And this slide number 10 and 11 are also explained in the recorded lecture. So on slide number 10, discussion is how to estimate uniformly distributed load of wall on the beam if wall is present. And like in civil department, you have noticed that there are number of rooms and there are beams running in the slab system, and in most of the rooms, walls which are dividing the rooms, they are directly resting on the beam stem. So those partition or dividing walls, if you will notice them, they are constructed exactly over the stem of the beam. So it means such walls will transfer their load directly to the beam. We discussed in the previous slides slab thickness, floor finish thickness, and pressures of occupancy, which are to transfer their load to the beam. And now the question is, what if something is directly resting on the wall? It means such a masonry wall, or there might be some other light partitions which are resting directly over the stem of the beam. So we can also include them in our load estimation over the beam. And so in next few minutes I will resume lecture from slide number 12 onward. It's simple that for masonry wall we will again use the density and the thickness of the wall and the height of the wall to determine the load per unit length on the beam. So the thickness multiplied by the height into the density will give us the line load on the beam, which I can add in my already calculated uniformly distributed load on the beam. Shall I resume recording?
Yes, sir.
Okay. If you have any questions, you are welcome. Or maybe next 1 hour lecture, you please first watch the recorded videos and then you can question me during that 1 hour interaction next week. So lecture is being recorded. So I resume that on slide number 10, the discussion is on how to include masonry load, masonry wall load on the beam. In this one slide, it is simply explained that you need to use the density of the masonry. You need to decide the thickness of the wall. If it is 9-inch thick, 28 millimeter wide wall, or thick wall, or 114 millimeter or 4.5-inch thick wall, partition wall, accordingly you will decide TW. Since we are using SI units, so we normally use 228 for 9-inch and 114 for 4.5-inch, one brick width. So height, normally if in our normal building story height is 3 meter, so H is 3 meter. This TW you will put in millimeters because 1000 is divided, so it will be converted into meters then. So here you will put TW in millimeter, H in meters, and density 1930 for masonry selected, It is in kg converted into Newton divided by 1000 into kilonewton per meter. So this simply will give you what is the masonry wall load per unit length service. Then obviously you will multiply this with 1.2 if you are working on ultimate stand design to convert it into ultimate wall load on the beam in kilonewton per meter. So earlier calculated WU, which was also in kilonewton per meter, you will add this wall load in that earlier calculated if there is a wall present. If there is no wall present, then don't include it. So if it is present, then you can include it. And furthermore, in some cases we have openings, and above openings we have masonry courses, and then finally the roof slab is present. And since masonry courses are such arranged that load distribution is at 60°, so it is safely assumed that above that small beam I will have to construct a triangle with the interior angle 60°, and within that triangle all the masonry courses weight will be included, which will be subjected to this lintel as the uniformly distributed load. So to convert this triangular load into equivalent UDL, a factor of 4/3 is used, and which is adjusted in this calculation. So in order to estimate the masonry courses load on the short beam, which is lintel, over the opening, this equation will help you to calculate the uniformly distributed service load, that you need to decide the thickness of the masonry wall over the lintel like we did on the previous slide, and you need to multiply it with the length of the lintel to get finally the service load on the lintel, and finally you will multiply this with 1.2 to convert it into UDL ultimate. It is mentioned underneath that if the apex of the triangle uh, is being intercepted by the slab above, suppose the slab is at this place and the complete triangle is not being intercepted, then you have to assume the entire slab load over the lintel, because now this apex is not well below the slab height. So if there are few courses above and then directly the slab comes and you are unable to get the full triangle before the intersection of the apex with the slab, then the masonry courses plus the slab load as we earlier calculated for ordinary beam will be used to calculate the load on the lintel. So then it means lintel will act like a beam because that lintel is very close to the slab. So few masonry courses which are present above the lintel as well as the entire slab load will be transferred to the lintel, and it will be like the ordinary beam which is present in the slab and taking the share of the load. So just give me few minutes, please. Discussion is uh, explained in detail in slides, recorded slides. Now, what I have explained in the first 8 or 9 slides is reviewed here from slide number 12 onward on some tentatively assumed slab loads over the roof. For example, on slide number 12, let me assume that the slab thickness of the roof slab, if it is 125 millimeter, 5-inch thick slab, and over the roof slab, we normally put earth filling of 4-inch thickness. And then on the roof slabs, there are brick tiles. So this is a common roof treatment. So for very ordinary, typical roof slabs, there is a summary of the corresponding you can say slab thickness, earth filling, and brick tiles, and their corresponding densities for the concrete, density for the earth filling, density for the brick tiles is used, multiplied with their corresponding thicknesses, and then they are summed up to estimate the service self weight over the roof slab. Similarly, if I have for this roof slab the proposed load over the roof, which is 200 kg per meter square as the life load, which is normally considered over the roof slabs, lightly loaded roof slabs, then underneath is given according to ultimate stand design that you are combining the service dead pressure, service live pressure with the combination of 1.2 dead plus 1.6 live and converting them finally into kilonewton per meter square. You are getting over the roof slab an ultimate load of around uh, 10 kilonewton per meter square, 9.66 kilonewton per meter square, or around almost 10. In our example problem, we got 11.65 when I selected the slab thickness 150 millimeter, and for intermediate floors, now they are assuming the slab thickness 150, screed, which is brick ballast plus 25% sand. So normally it comes from architecture working drawings that what they are planning in terms of floor finish. It is 75 millimeter. You can say screed, PCC 40 millimeter, above that screed, and terrazzo floor 20 millimeter. And for this entire composite of screed, PCC, and terrazzo, we need to decide the corresponding densities. For screed, which is relatively of less density, the proposed density is 1800 kg per meter square. However, PCC and terrazzo are little dense, so for them the proposed density is very close to concrete. It is 2300 kg per meter square. So out of this composite, the slab 150 is calculated by 2400, then comes screed, and then terrazzo plus PCC almost having the same densities. So in this way, we can get total dead load on the total dead service load on the slab. So in this way, we will have the final estimation of ultimate loads on the intermediate floors. But here they are also explaining that if for intermediate floors, the proposed occupancy load is 250 kg per meter square. I earlier used 300 kg. So this is also for some residential buildings, intermediate floors. 250 is quite safe. So if they are considering 250 kg per meter square as the occupancy load here, but in addition to this, in some floors, there are movable partitions as well, which are non-load bearing walls. and they are not permanent. So in some cases, it is advised to consider such additional load over the floor, intermediate floors, to add this movable partition. The idea is to first calculate the volume of that partition. You know the thickness of the walls, their lengths from architecture working drawings. You know the height of them as well. So knowing the volume, you can multiply it with density. That will give you total weight of that partitions. Then divide that total weight with the area on which they are resting. It can be converted then into pressure. A very conservative light partition, movable partition load proposed here is 150 kg per meter square, and it is considered along with the live load. So if it is bracketed with the live load, it means it will finally get a load factor 1.6. So in some cases, you may put the partition load along with the dead load to get the load factor 1.2. Here they are quite conservative in selecting the movable partition with the live, because when you are putting something with the live, it means you are getting more load factor for that. It is normally decided based on the type of the building, that how much alterations or variations they are going to make, and whether the partitions will remain the same one, lightweight, or they may altogether change the type of partition. So in this way, normally exact drawings are required, and their location of the walls, type, thickness, height is known, and then using the densities we can calculate the load of total additional walls, which are although non-load bearing, but their load will be present on the slab, and that slab load will be transferred to the beam, and then from the beams to the walls load bearing, or to the columns load bearing, to and through them to the ground underneath. So their portion should also be included in the estimation, and here in this example they are proposing you a very light ordinary partition pressure of 150 kg per meter square. So together then, and combining them in combination, we are getting a ultimate pressure on intermediate floor of around 14 kilonewton per meter square. Earlier we calculated 11.65, in which partition was not involved, and there was a floor finish of 100 millimeter. So as I said earlier, around 12 to 15 normally you will get the ultimate pressures on such ordinary slabs. Then beam also has some cross section, it has some projection below the slab. The stem load of the beam is also very important, and will become quite big in case if beams are deep. So ignoring the self weight may get little dangerous if the beams are having big cross section, because when you are estimating the self weights of the slabs, floor finishes, you are not including the drop of the stem of the beam below the slab. So here now self weight of the beam estimation is explained. It is simple. If you know the gross H of the beam, you can subtract from that gross H the slab thickness, because slab thickness is already included in the estimation of the slab load over the beam. Then you know the width of the beam, You can multiply it with the density, and in this way you can get per unit length the self weight of the beam in kg per meter. And finally you can multiply it with 9.81 divided by 1000 to convert the self weight into kilonewton per meter. They are actually working on a typical cross section that if B is having the relationship with span by 12 and H has the relationship with as span over 18, and for per meter length you are estimating the self weight, so you may get such kind of equation. So if you have already decided the width of the beam, the H of the beam, then no need to use these variable, you can say B and H. You can tentatively select B and H well before estimation of the self weight. So rather than using this equation, you can intelligently include the self weight of the beam by fixing the cross section first. If you want to just use it for estimation, then this span by 12 for B and span by 18 for H will be a good choice for B and H. And then finally you will also multiply this self weight with the corresponding load factor, which is 1.2, and also to convert it into kilonewton per meter you will multiply it with 9.81 divided by 1000. So I think I will stop today's lecture at this slide number 17. So I recommend you to please go through the recorded videos, and next time then I will discuss a bar bending schedule, how to calculate the weight of the steel from the structural drawings. So that is actually explained in the next few slides from slide number 17 onward. So I will start next lecture from slide number 17 onward. I have shared with you PDF file of this lecture and the recordings as well. So please go through them so that next time we can finish the bar bending schedule as well. And then as homework, please solve all the solved and unsolved problems in chapter number 3 given in SI edition. All those examples which are in SI system of units you are going to attempt. In FPS system there are some examples which are repeated. Don't consider them in your homework. Just repeat those problems solved and unsolved which are in SI system of units. Agreed?
Yes, sir.
So this hour of recording is also uploaded, and you are almost 40 at the moment. So please watch videos and then let me know if you face any problem in understanding. You can text me on MS Team, or otherwise in start of next lecture you can stop me and you can ask me questions. about a minute ago and about 41 minutes ago. The latest recordings are arranged here. So let me end today's meeting. Okay then, Allah Hafiz.